Good afternoon, everyone. It's an honor to be here. I'm Jiahe. This is a joint work with some collaborators from Beihang University and the Chinese University of Hong Kong. The title of our paper is VILAM. It's about a new paradigm that leverages smart roadside infrastructure to assist the localization and mapping for autonomous vehicles. Localization and mapping are two critical components of autonomous driving. The vehicle needs to precisely and continuously know where they are and to perceive what the road environment looks like. As we can see, localization and mapping module are at heart of autonomous driving software frameworks. A key challenge of this component is to achieve decimeter-level accuracy. However, existing navigation map products, such as Google Maps, can only provide accuracy of about 10 meters. Motivated by this huge performance gap, there has been intensive work on high-accuracy localization and mapping. One of the most promising solutions is SLAM. SLAM technology utilizes video streams from cameras as input, reconstruct an online 3D map of the unknown environment, and simultaneously determines the camera's position and orientation within their surroundings. It holds the potential to enable the critical localization and mapping tasks required in autonomous driving system with very low-cost sensors. It's attracting increasing interest in both industry and research community. However, a key drawback of SLAM system is that the localization and mapping errors can accumulate over time. These errors are usually caused by two major reasons: the inherent distortion and noises of sensor, and errors from image processing components, such as feature point extraction and feature matching. This error may be moderate at short distance, but as the vehicle travels further, they accumulate frame by frame over time and cause significant cumulative drift in the constructed map. To illustrate the impact of the cumulative drift, we conduct a real-world experiment, as shown in this photo, where a test vehicle mounted with a camera drives through compass road, denoted by the yellow line. Here we show the real-time localization and mapping result using a state-of-the-art SLAM algorithm. We can see that the cumulative drift exceeds over 10 meters for both localization and mapping after only a 500-meter drive on the road. Well, apparently this level of error is not acceptable for autonomous driving vehicles. So to handle such drift, most existing solutions use a technique called loop closing. Well, specifically, when vehicles revisit a previously traversed area, the loop closing method aligns the current map to the history map. Such alignment allows it to eliminate the cumulative error. Well, usually this method is used for robots to navigate in small-scale indoor scenarios, where the trajectory of the robot can always form a closed loop. However, in driving scenario, most vehicles travels from location A to location B without any closed loops. So as a result, the solution is not very practical for SLAM in autonomous driving. Well, as another way to deal with the cumulative drift, we might continuously use GPS positions to correct the error during driving. However, consumer-grade GPS is not accurate enough, while the high-precision localization devices are extremely expensive, or for example, up to $4,000 per unit, way more expensive than the cameras. Moreover, it's well known that GPS can fail in many scenarios, such as underground parking lots. Therefore, how to make SLAM accurate enough for autonomous driving is still an open question. So our key observation is that two types of information are required to eliminate the cumulative drift. The first one is prior measurement of the environment, such as the history map from the loop closing. While the second one is external localization, such as the localization from the GPS device. Now the important question is how to find and combine these two types of information to achieve accurate SLAM for autonomous driving. Here, our key idea is to leverage the smart roadside infrastructure. Nowadays, roadside infrastructure, such as a smart lamppost, has been widely deployed for many applications, such as traffic monitoring and driving assistance. They are usually equipped with 3D sensors, such as LiDARs and computing devices. The LiDAR on the infrastructure can capture accurate 3D measurement of the surrounding environment. But moreover, because the infrastructure nodes are stationary, we typically know their precise locations. Through V2X communication, this information can be transmitted to the vehicle in real time, which can help the vehicle to effectively reduce the cumulative errors in SLAM. Based on these ideas, we propose VILAM, the first system that can leverage roadside infrastructures to realize high-precision localization and globally consistent mapping for autonomous driving vehicles. The key idea of VILAM is using the accurate scene measurement from the distributed infrastructures as global reference to correct the cumulative drift of vehicle SLAM. Here is the pipeline of VILAM. First, on the vehicle side, we employ existing SLAM method to the onboard sensor and continuously update a 3D local map. On the infrastructure side, we periodically extract a lightweight measurement from the infrastructure LiDAR point clouds. The measurement encodes the planar features of the static objects in the surroundings. When vehicles pass by the infrastructure, the measurement and the infrastructure location are broadcast to the surrounding vehicles and utilized as global references. Once the vehicle receives the global reference, a novel elastic registration approach is utilized to align the latest vehicle map with that reference. This process corrects both the local map and the vehicle's trajectory. Finally, VILAM builds a globally consistent map based on the corrected map and the trajectory of the vehicle. Next, I will briefly introduce the key modules in our design. Recall that on the vehicle side, we continuously build and update a local SLAM map, which is deformed due to cumulative drift. So, after obtaining the infrastructure measurement, how do we correct the vehicle map and the trajectory? When vehicle is passing by an infrastructure node, there is usually a significant overlap between the views of the vehicle and the infrastructure. Therefore, we can align the point clouds of vehicle map and the infrastructure measurement. This process is typically referred to as point cloud registration. Here, the major challenge is, due to the cumulative drift, there is irregular deformation in the vehicle's local map. Conventional point cloud registration method assume that point clouds are rigid bodies. Therefore, they only estimate the rotation and translation between two point clouds. When we apply such registration method, only part of the map can be aligned and corrected, but the deformed part still has large misalignment. Therefore, we propose an elastic registration method to solve this problem. The intuition here is to align each point from the point cloud independently when doing registration. We introduce two types of constraint to get the registration. The first one is geometric constraint. For the points from two point clouds that belongs to the same object, it ensures these points are aligned together. Second one is visibility constraint. It ensures that same point observed from different positions of the vehicle's trajectory remains consistent. Based on the joint optimization under both constraints, we can make sure each deformed part of the vehicle map is corrected, and we can accurately align the map with the infrastructure measurement in an elastic manner. However, only aligning the local map with the infrastructure is not enough, because the roadside sensors usually cannot achieve continuous coverage of the road. Therefore, despite the gaps in the sensor coverage, we need to piece together the corrected maps to form a globally consistent map. Here we propose a lightweight vector graph-based approach to address this problem. Specifically, we represent the 3D poses from the vehicle trajectory as the graph node, and we represent the trajectory segment that corrected by the infrastructure as the constraint factor. Then we use the frame-by-frame transformation as the graph edges to connect nodes from the covered and the gap area. As a result, through factor graph optimization, the map correction from the infrastructure covered area can be efficiently propagated to the gap area along these edges. By retrieving the optimized poles from the graph nodes and update the corresponding map points, we can finally construct a globally consistent map. We evaluate VILAM on real-world testbed across diverse driving scenarios, such as open roads, underpasses, and underground parking lot. Each of these scenarios poses challenge for existing SLAM system. The figure on the right shows the prototype of infrastructure nodes we designed and the test vehicle used in the evaluation. The data we collected covers over 17 kilometers of driving trajectory with over 40 infrastructure nodes. This is an end-to-end evaluation we conduct in the underground parking lot. The upper figure shows the floor plan, driving trajectory, and the locations of the infrastructure node. The middle figure shows VILAM's localization error in real time during driving. The lower figure shows the mapping error. Here we can clearly see the benefit of the infrastructure. When vehicle passes an infrastructure node and receives a global reference, VILAM quickly corrects the vehicle trajectory and map, resulting in a notable reduction in real-time localization error. These two figures show the runtime latency of VILAM and the breakdown of delays of different modules. Most of the time, VILAM typically execute only the local map construction task within 60 milliseconds. The elastic registration and the global map correction are performed after the vehicle receives the measurement from an infrastructure node. This spend less than 300 milliseconds in completing the total map correction. In our design, the two modules triggered by the infrastructure runs in parallel with the local map construction module, so VILAM can still generate localization and mapping updates at a frequency of over 10 Hz. This ensures the real-time performance of VILAM. We also evaluate VILAM's performance under different infrastructure coverage. As we can see, although the error arises as fewer infrastructure nodes are deployed, VILAM outperforms the baseline by a large margin. The average localization error is less than 0.5 meters under only 20% infrastructure coverage. This figure shows the accuracy of the map and trajectory result of VILAM. Overall, VILAM can effectively reduce the cumulative error of existing SLAM method and provide vehicles with decimeter-level localization and mapping accuracy. Finally, I'd like to show a video demo of VILAM.
Cameras. However, existing visual SLAM suffers from cumulative drift as the vehicle travels. VILAM proposes to leverage the precise scene measurements from LiDAR sensors on roadside infrastructure to enhance visual SLAM. VILAM aligns the map constructed by the vehicle with the infrastructure measurements to correct both the vehicle's trajectory and the map. VILAM achieves accurate localization and mapping by opportunistically harnessing the measurements from distributed infrastructure nodes. In contrast, conventional visual SLAM systems can exhibit an increasing drift after a long-distance driving.
So from the result map, we can see clearly that the structures from VILAM's map are more accurate than the drifted SLAM map. So in conclusion, we propose a new approach for autonomous vehicles to leverage the roadside infrastructures to achieve accurate localization and mapping. We designed some techniques to address the deformation of the SLAM map and the incomplete coverage of the infrastructure nodes. Overall, VILAM can achieve decimeter-level accuracy for real-time SLAM. So thank you very much for listening. Now I would like to take some questions.